Just a few words of introduction. As far as I'm concerned, I'm David Eaton, and my role at the Hawley Tool Collection is looking after the metrology collection. We've got a fantastic metrology collection. If you go around the Hawley collection, gallery, you won't see it. But if you go through the gardens, through the gates, turn right, you go into a place called the Sedgley Building, and in there we've got a metrology section, and we've got in the collection over 300 micrometers, all different, and we've got more micrometers than the Science Museum. So if anybody's interested in looking at that collection, we've got more than micrometers, by the way, just contact me at the Hawley Tool Collection and I can show you around, or one of my colleagues like Mark can show you around the collection. So I'll start with the presentation. We're going to look at the products that 3 companies in Sheffield manufactured during the late 19th century and up to the middle of the 20th century. Sheffield at that time was a centre of excellence in precision engineering. I know that most people think it was all to do with heavy steel and heavy industry. It wasn't. The 3 companies in Sheffield that were really at the leading edge at that time were Shardlow's and Shardlow Metrology, a company called Moore Wright, and a company called James Chesterman. Now, how do we define precision? Precision is, if a company is a precision engineering company, it can actually manufacture products to a tolerance of 1 thou. I work in inches, by the way, not millimeters, and 1 thou or better than 1 thou. And 1 thou, your hair, if you've got hair, if I can find mine, it's about 4 thou. If you measure your hair, it's about 4 thou. So 1 thou is a very, very small distance, very small distance. So that's how and I used to have a lot of discussions with Ken Hawley about how do we define precision, and that's the definition that we came up with from a discussion I had with Ken. Ken, that's Ken. And Ken died in 2014, a sad loss to the collection because Ken knew more about tools than anybody. And if you brought a tool in that looked very obscure and said to Ken, "What's this tool?" Ken would know. And he was very proud of the metrology collection. He went to companies when they were closing down and managed to get hold of their products that they was thrown in the dustbin or thrown in the skip. And Ken went to Shardlow's, he went to Moore Wright, and he went to Chesterman, and managed to get some phenomenal micrometers and measuring tools from these companies. So we've got a lot to thank Ken for. It's a small collection of the micrometers that we've got in the collection. The one at the top there, on the left-hand side, is the oldest micrometer that we've got in the collection. That's the micrometer there. That's the micrometer. That's the oldest micrometer in the collection. It's very difficult to read. It works on inches, but that is the oldest one. That's the oldest one. We're not sure, actually. There's really no information, but we think it was about the 1850s, something like that. The maker's unknown, the date is unknown, but round about 1850. A micrometer screw thread was first used in the 1600s. People started to realise that if you had a screw thread and you knew the pitch on the screw thread, you could move a spindle a certain distance. And it was a man I've forgotten his name actually, a man in Yorkshire that used micrometers. He was an astronomer, and he used a micrometer to gauge the diameter of the moon and diameter of... so that was the first use of micrometer screws. That is a copy of a screw caliper based on the design of a chap called Palmer, done in France. And you can see the basic design is similar to the very early micrometer. That belongs to me, that particular micrometer. That's not a Palmer micrometer, that's a copy of it. But Brown and Sharp went to an exhibition. Brown and Sharp is an American company, by the way. That's Brown and Sharp. They went to an exhibition in the States, I think it was 1857, and saw that, the Palmer micro, and decided that they were going to manufacture it within their company, manufacture micrometers within their company. That is another micrometer. That Ken was very proud of this one, and that's graduated, so you can measure the weight of glass with that micrometer. And we think that that one was used in the Great Exhibition in 1851, because there they made this building with glass everywhere, and they wanted to know whether the structure could actually carry the load of the glass. So they needed to be able to measure based on the thickness, the density of glass, so you could actually determine the weight of glass per square yard or something like that. That's a very, very early micrometer of Shardlow's. By the way, I'm talking about micrometers. Is everybody aware in here of what a micrometer is? A micrometer is a tool for measuring very accurately metal or metallic components. And by rotating the thimble, you can actually, if you know the pitch of the screw threads on it, by rotating the thimble, you can establish the distance that the spindle moves from the anvil. The three Sheffield companies were James Chesterman, that was based at the Bow Works, bottom of Ecclesall Road. You're probably well aware of that, and probably people in the audience work there. Shardlow micrometers, and you can see the sort of range of tools that Shardlow's made, and Moore and Wright. That was the best catalogue picture I could get for Moore and Wright. Right, we'll talk about Shardlow's. I couldn't find a picture of Ambrose Shardlow. I don't think there's a picture anywhere. I went to Sheffield Archives, I looked all over, Keith looked all over the web for me. But that's a picture of his son. So whether the father looked like the son, I'm not sure, but I would imagine that there was a similarity there. And you can see that Arthur Shardlow lived from 1877 to 1958. So he was really the driving force behind the Shardlow company. That's a photograph of the main gates of Ambrose Shardlow. I haven't got a photograph of Shardlow Metrology, which is a different building on which was a different building on Peter Street. But that was the Ambrose Shardlow. You're probably aware that Ambrose Shardlow made crankshafts. They were experts at forging and machining crankshafts. And I'll talk a little bit about the history of how micrometers came about at Shardlow's. And on there you can see a large micrometer, a height gauge, other types of gauges, internal bore gauges, internal bore gauge, another internal bore gauge there, a straightforward micrometer. That's a micrometer head that would be used on a machine table, and that's a depth gauge. When Sheffield decided they were going to manufacture micrometers, they didn't start from square one. What they wanted to do was find a micrometer in the world that they could copy. So it was a bit of transfer technology or copyright issues that must have played a major part at that time. But Shardlow decided, having done a lot of searches on different micrometers, they decided that the Slocum micrometer was the sort of micrometer that they would like to copy. So they used that as a basis for their design. That's what a micrometer is. And they were first used in a major way in the First World War. In the First World War, Britain got all its micrometers from the States, not from, there was no place in the UK that was making them in the First World War. And because of the invention of the internal combustion engine and very precise engineering components, they needed instruments that could measure very accurately the component parts, so they fitted together. And so it worked well. And the British government decided that we needed to make micrometers in the UK. Shardlow's at that time had made micrometers for their own purposes. They designed and manufactured micrometers in their own works, which was, I think it was Washford Road in Sheffield at that time, before they moved to Meadow Hall. And the government asked them to produce a range of micrometers. That's how it started at Shardlow's. Shardlow's were very innovative in their micrometer design. They made a range of different micrometers, And you can see on there, if I can use it, can you see how the markings there are at an incline? Rather than being straight across there, they're at an incline. That was supposedly to enable the operator, the person that using the micrometer, to be able to see the divisions more clearly than if they were vertical. Now, I don't know whether that works or not. I've not tried to use that micrometer in anger, but that was one of their innovative design it's called the oblique micrometer. That is known as the check reading micrometer, another innovation that Shardlow's came up with. If you see on there, you can see all the markings on there. You would read that by counting the number of divisions on there and then identifying which particular numbers lined up with that, they call that the fiducial line, or that line that runs down there. That was, again, supposedly to enable the engineers that were using these micrometers to be able to read them very simply. Micrometers are very simple to use, by the way. I know that people think they're complicated, but they're not. All it is a spindle. You've got your spindle there, you've got what you call your thimble there, and you've got the barrel there. And if you rotate the thimble through one rotation, the 40 threads per inch, one rotation gives you 25 thou movement in the spindle head there. So they're very straightforward to use. I know that when I was an apprentice, I struggled to read it, but by the time you get familiar with them and you're using them, they're very straightforward to use. Shardlow's also made height gauges. That's an instrument there that will measure the height from the bottom face there, which is on a surface plate, engineering surface plate, to that particular probe at that point there. Now, Shardlow's made these height gauges, so did Chesterman's, and so did Moore and Wright. And I'll come on to that story in a minute. I've got my own copy of a Shardlow vernier height gauge at home. We haven't got one in the collection. We've got a model of the base that we think salesmen used to take round to sell their height gauges. But the problem with a height gauge, it's based on what they call a vernier scale, not a screw thread, it's based on a vernier scale. You can only read to 1/1000th of an inch, whereas with a micrometer, you can read to 1/10 of a thou. You can only read to 1 thou with a vernier height gauge. That's another photograph of the same height gauge. You can see that scale on there. You can see the vernier scale on there. As you unscrew that, you can move that up and down, and you can put your component in here from the surface plate and get a very, very accurate dimension of the height. Right, this is a very interesting micrometer. This is called the anglometric micrometer. And supposedly the beauty of that is it will read both in metric and imperial dimensions. If you see across there, you've got this inclined scale. By reading that inclined scale on there, you can get the metric dimensions. By reading the horizontal along the fiducial line there, you get the imperial measurement. Now, both Ken and I tried to use this, and it's a very complicated thing to use. You can soon get confused about which you're reading. So I don't think that innovation took off that well. Eventually, micrometers, because people found them difficult. Some people found them difficult to use. The unskilled people within a company probably found them difficult to use. Shardlow decided that they were going to try and design one where you'd got numbers which are in that little magnifying glass there. So if you turned it round, it gave you a dimension in there. And that was called the MISI, and it was after an American inventor. So you can see how Shardlow was copying other companies, American companies. The problem again with that design, we do have one in the collection. This was a photograph from one of my friends. That design was very, very difficult to read. You need good eyesight to be able to read the numbers in there. Very good eyesight. So again, we don't think that that was a very successful innovation. This was a better innovation. Again, this was based on a Slocum micrometer. And you can see on there the numbers in these little windows. And that gave you the tenths, the hundredths, and the thous. So all you had to do there was to be able to read 3 numbers. But you could also, if you didn't trust those 3 numbers, they've also got the standard micrometer markings on the side there. Now that micrometer is called a speed read. That was produced for a while, even when Shardlow's closed. That was produced by, manufactured continuously after that for a while. Right, let me just talk a little bit about Shardlow's, Moore and Wright, and Chesterman's during the Second World War. The government needed lots and lots of micrometers for precision manufacturing, and the problem is that we got the micrometers either from America or Germany. We're at war with Germany, so we can't get their micrometers. The trouble is getting micrometers across the Atlantic from the States was difficult because of U-boat attacks. So the government decided that they wanted lots of micrometers manufactured within the UK. And they looked at these 3 companies in Sheffield, and they decided that Moore and Wright were the experts at producing micrometers. Not Shardlow's and not Chesterman at that stage. So they asked Moore and Wright to concentrate on micrometer manufacture. They then asked Shardlow's and Chesterman to focus on the linear measurement, the vernier scales. So you can see how the government then started to control the manufacture of precision engineering measuring tools within the UK, and within Sheffield in particular. Right, let's move on to Chesterman, James Chesterman. The original company, as you may be aware, was formed in 1857 by a chap called William Chesterman. There's no pictures of William Chesterman, but James Chesterman took over the company from William Chesterman. I think they were based on, is it Nursery Street in Sheffield when they first started in 1857. It was called Bow Works then, and they manufactured tapes, land chains, other sort of non-precision tools. But they were the first to produce metal tapes, linear tapes, and they had some fantastic equipment to produce these long tapes. Eventually, after the Great Flood of Sheffield, it took away the factory. They moved to the bottom of Ecclesall Road. And Ecclesall Road, the Bow Works was set up on Ecclesall Road. And that is a picture of the gate to the Bow Works on Ecclesall Road. Chesterman, by the way, were a fabulous engineering company. One of the best precision engineering companies, probably in the UK. That's a picture of, that's a drawing of the Bow Works there. That is a display cabinet that we've got in Hawley, and I'll tell you a little bit of the story of that. That display case shows the vast majority of that were made by Chesterman. Ken bought that off eBay, and we got that for £500, I think it was, off eBay. It was a good buy that. I think these days, if you tried to buy that for £500, you wouldn't get it. We tried to buy a Moore and Wright one, and we put a bid in for £2,000, and we didn't get it. Someone else managed to beat us to it. But on there, you can see the range of precision tools that Chesterman manufactured. And you can see the height gauges there, and you can see all the engineer's triangle angle there. The depth, that's a depth gauge. That's a combination square. You probably use those in your woodworking work at home. These are precision tools, by the way. So you wouldn't use that for woodworking. You'd use that for making precision metal components. A thread gauge there, which you can measure very, very close dimensions. You probably use those on your car, measuring the plug gaps on your car. Micrometers, angle, 90-degree angle, calliper. So you can see they made a fantastic range of precision engineering components. Chesterman wanted to start to make micrometers. They made their first micrometer in 1937, so it was later than Shardlow's. And again, Chesterman wanted to copy a good quality micrometer. And they looked at a range of micrometers, American again micrometers. They looked at the Slocum micrometers, they looked at Kalmar micrometers, they looked at Johansson micrometers, and they decided to use the Kalmar micrometer as the basis of their design. Now, a story of this is when they were closing the factory down, Ken realised they were closing the factory down and decided that he wanted to get more equipment from Chesterman's, and he wanted some idea. He'd heard about this micrometer from a chap that used to work at Chesterman's, and this guy said to him, I've forgotten the man's name, if you get hold of a micrometer from Chesterman, try and get hold of the Kalmar micrometer that they use as the basis of their design. Ken went to see this person in Chesterman's, went into this manager's office and sat down, and Ken then explained what he was after. And he said he'd spoke to this chap that used to work at Chesterman's, and he wondered whether or not he could have a look at the Kalmar micrometer. And as they were talking, the chap opened his drawer and brought out these three micrometers, a Johansson, a Kalmar, and a Slocum micrometer. He says, these what you're looking at, what to look at. So Ken said he looked at them and drooled over this Kalmar micrometer. He said when he picked it up, it was like silk when he turned it. He said there was no play whatsoever in the screw thread. He said he could have played with it all day, that micrometer. Anyway, Ken, after the discussion, gave it back to the chap. And the chap said, well, you might as well keep these then now. He says, because we don't want them. He says, nobody want them here. So Ken managed to get hold of those three micrometers. And that is the Kalmar one that we've got in the collection. Chesterman manufactured three different patterns of micrometers, only three. Top quality, we have copies in the collection. They had a 0 to 1 inch micrometer, a 0 to 25 millimeter micrometer, and a 25 to 50 millimeter micrometer. We've got all those in, but they only manufactured three. Now, Moore and Wright were knocking them out by the thousands per week. Chesterman were very precise. They used very accurate techniques to manufacture the screw thread. They used a rolling technique to manufacture the screw thread, which was very, very accurate indeed. And they are beautiful instruments to use. But they only made them for a short time. And in the catalogue, that's the only page in all the catalogues that we've got in the Hawley collection that shows the micrometers. And it was at the time that the government has said to Chesterman's, don't make any more micrometers. Moore and Wright are the experts in making micrometers. You focus on height gauges and vernier calipers. which was a pity because though they stopped manufacturing them, they hadn't got spare parts. After the war, they decided to use these parts to make the micrometers again for a short time. But it's a pity that happened with those micrometers. That, by the way, there is that's a 25 to 50 millimeter micrometer. And to calibrate that, you need a very accurate calibration piece within there that's 25 millimeters. When you've got that micrometer there, you can close it up and you can zero it. But with that, you can't zero it, can you? Because that won't meet there. So you've got to use a very, very accurate calibration piece to do that. Those were the three types of micrometers that patterns. That would be there at the top one. I think that's the 0 to 1 inch micrometer. That's the 25 to 0 to 25 millimeters micrometer, and that's the 25 to 50 millimeter micrometer. The problem is that they were very, very expensive to manufacture. They were very accurate to manufacture. They needed precision to manufacture them, and the cost was very high. So compared with a Moore and Wright micrometer, the cost of Chesterman micrometers was 3 or 4 times the cost because of the precision that they used in manufacturing them. I don't know whether they've ever used the Moore and Wright micrometer, but sometimes they can get a bit stiff and a bit wobbly, a bit stiff. Whereas you don't have that problem with those. Chesterman height gauges. Chestermans were experts at manufacturing vernier calipers. And if you look at that, or you look at this model, you can see that on there you've got very accurate graduations along there. They had to be made absolutely precise because it's no point in having an accurate tool if the graduations on it are inaccurate. And in 1909, they bought what they call a calibration machine, a dividing engine that divided very accurately these graduations, and it was an SIP, a Swiss manufactured machine. We've got one in the collection. Again, Ken got these from Chesterman's when they were closing down. It's a massive piece of equipment, and it allowed Chesterman's to graduate that column there very accurately, and also graduate the vernier scales there. Vernier scales, by the way, are quite complicated in terms of how they work, but you can actually measure to 1/1000 of an inch in terms of using a vernier scale. Again, that's a picture out of their catalogue, and that was the creme de la creme of Chesterman height gauges. We have a collection of height gauges. That there is the 48-inch one, but it shows the range of height gauges from the very, very early ones that they made to the final ones that they manufactured. That one there, if you can see it, is one of the very, very first electronic height gauges. These days, there's been a move from mechanical analog precision measurement to electronic precision measurement. When the Japanese got involved in it and started manufacturing electronic height gauges, a lot of this went. They wouldn't use these in industry now. They'd use the electronic ones. I don't think that was a big success. It was bulky. Whether it was accurate or not, we're not sure. And it won't work, so we can't try that one out. But they obviously realised that there was a move towards electronics from analog, from mechanical type height gauges. That's a Chesterman height gauge, and it was designed by one of their top designers called Tom Bailey. Tom Bailey was a brilliant engineer, and if you look at the height of, if you look at the cross section of that height gauge, you can see that it's triangular in shape. And the reason it's triangular in shape is to reduce the amount of deflection you get on the column. Up to that point, before Tom Bailey came up with that design, height gauges were rectangular. The column was a rectangular shape. So if you got above 12 inches, it was about 12 inches, you started to get deflection because you put in some load on there. You put in a load on that. That's the probe that measures the height, and you're trying to measure to 1,000th of an inch. So a very, very tiny amount of deflection on that would make the reading inaccurate. And what they needed to do was get an accurate height gauge up to 48 inches. And Tom Bailey came up with that cross section. Now you can also see that Moore and Wright have got a similar cross section to that. And I just wonder whether they copied the Chesterman design. I don't know how it worked in those days. We do have examples in the collection of measuring tools that have been made by both Moore and Wright and Chesterman together. So they've obviously worked together to produce a particular measuring tool. But whether that was a copyright issue or whether they got permission from Chesterman's to use that cross section, I don't know. But that is an example of a very, very innovative design to get 48 inches of measurement. Chesterman also were involved in manufacturing steel calipers. And a steel caliper is like a height gauge, but it's much smaller and you can measure smaller objects with it. That is one of their, again from their catalogue, and I'll show you some photographs of the very early ones. That's one of their very, very early calipers. And you can see what they've done there. They've got a fixed end at that point there, and they've got this particular part of the caliper attached to that fixed end. You've then got this movable piece here. So you can move that along there, and by reading off this scale, you can then read the dimensions across here, across this distance. You can see what they've done. They've used a straightforward rule for that. So in terms of the calibration of that, it wouldn't be terrifically accurate. They wouldn't be able to measure to 1,000th of an inch with that, because I think the best you could get was probably 64th of an inch with those scales there. But that's a very, very early gauge using an engineer's rule. And you can see how these innovations develop. The next one shows a step up from that. You can see they call these nibs, by the way, nibs here. And again, it's a similar rule there, but that's in centimetres, millimetres and centimetres. And you can see the nibs are starting to look like the modern design. That's the ultimate in their linear vernier scales. And you can see it's got metric on one side. It's got metric, I think, there and inches there, so you can read. And what you're doing, you're reading that distance there. You can see it's different from a micrometer. A micrometer requires the screw thread to be accurately manufactured. So as you turn the thimble round, the screw thread moves at one pitch, one distance along the axis of the screw thread. And if you know precisely what the pitch is of the screw thread, you can then get a very accurate dimension. That's the micrometer. With this, it's a sliding mechanism. And you can see there that as that slides along, you can fix it, and then you can move this very accurately, so you can get a very accurate dimension. All these have disappeared in the engineering workshops now, unless you're in a very old engineering workshop. It's all gone electronic, and you can go into, I don't know, B&Q or somewhere like that, and you can buy an electronic caliper now for £6, £7, £8, something like that. Very, very cheap. Very accurate as well. The electronic ones that you can buy now are very accurate. The problem with this is, I don't really know the company called Mitutoyo, which is a Japanese company that makes top quality precision engineering measuring tools. The problem with a vernier, it doesn't follow, I'm going to baffle you a bit now, with what they call the ABE principle. A micrometer does satisfy the ABE principle, where you're measuring along the axis that you're fixing the component in. That's the ABE principle. This doesn't satisfy that, because you've got your component here and you've got your measuring scale there. So you can actually get deflections here. You put a component in there, you tighten it up too much, and it pushes one of these, it pushes one out and pushes that one in. So you get not an accurate dimension. That doesn't satisfy the ABBE principle, because on a micrometer you've got the axis of measurement in the same direction as the component that you're measuring. Right, that's a drawing of the SIP linear dividing engine, and you put that came out of one of the manuals for the machine that we've got in Hawley. The very expensive tools, these very, very precise Swiss engineering. You put the thing that you're calibrating on there, that's the head, that's their microscopes there. So as you move that along in that direction, you can then scribe lines, very precise. So the scribing head would be on there, the screw thread is through there, that balances it out. It's usually driven by an electric motor, these, electric motor. That is a diagram showing the way in which the calibration, that's the tracelet there that produces the markings on the scale. That there is known as a correction plate. That's the screw thread that runs along that. Sorry, that's the nut that runs along that screw thread. So as you turn that handle there, you can move it one rotation, and that will move that screw thread one pitch. The problem is, when you're making screw threads accurately, you can never actually get them precise. You'll never get them precise. So what they had to do was to correct the errors in the screw thread, and they used that. They produced what they called a correction template. In the UK, they'd have to send it to NPL, the National Physics Laboratory, and they would precisely calibrate that screw thread. And they would produce a correction bar to take out any errors in that screw thread. So as that nut is moving along, it's moving up and down here, so it's moving the screw thread backwards and forwards slightly to take out the errors in the thread itself. The errors are not massive, by the way, but they're sufficient to make the calibration inaccurate. And we've got one of those in the collection. I've often thought I'd like to strip it down and have a good look at how all this works, because it's a very complex kinematic design. The whole thing is very complex. As that moves along as well, but when it gets to a certain position, it draws a line. It gets to the next position, it draws another line. So it's the mechanism for doing that is very complicated. And I've often thought it would be nice to strip it down. The problem is I might never be able to get it back together again. So that's why I've not done it. Right, on to Moore and Wright. Frank Moore came to Sheffield, I think it was something like 1906, and set up a small works in Reed Street in Sheffield. But it was a small works in Reed Street, which is that works there. And they made basic engineering tools at Reed Street. They made engineers' spanners, hammers, chisels. So you can see there's no, it doesn't say where it is. They then eventually moved to Trafalgar Street, and that's the works at Trafalgar Street there. So they started to move from basic engineering products there, chisels, hammers, engineer squares, into metrology in this area here. I think they produced the first micrometer in 1931, so you can see it was well after Shardlow's. But there, and they moved eventually. You probably remember this, some people, at Handsworth. It's where Asda is now. I think it's where the Asda car park is. So they eventually moved there. And that's, again, a very basic catalogue of the tools that Moore and Wright made in very early on. Moore and Wright, again, decided they wanted to make micrometers. And they'd got no expertise in making micrometers. And they'd factored micrometers made by a company called Avia. And the micrometers were called Oriel micrometers. And I've got one at home, an Oriel micrometer. So they took that micrometer and they managed to get the engineering drawings from Avia. That we've got a set of these in the collection, which shows that's the frame of the micrometer, by the way. It's all in metric dimensions, and the engineers at Moore and Wright had to convert all those to imperial, and it's not an easy job to go from metric to imperial because you've got added errors when you're doing that. But that's the Oriel micrometer drawing that we've got in the collection. You see at the top there, the Moore and Wright micrometer, the first Moore and Wright micrometer, there. And there you'll see the Oriel micrometer. So you can see the similarity between the two. And you can see the ratchet similarity there, you can see the thimble similarity. The barrel is slightly different, and you can see these numbers on the Moore and Wright, which gives the metric equivalent of inches. That is a very early standard micrometer at Moore and Wright. For those who are left-handed, Moore and Wright came up with a left-handed micrometer. So you've got there a left-handed micrometer. It's quite difficult to use a micrometer if you're left-handed, because it's difficult to work with. We managed. Ken was always after that from a chap in Sheffield, and at Ken's memorial that was held here, and the guy came up to me and said, Ken was always after this. He says, you can have it for the collection. So it's a beautiful micrometer, but it's for left-handed engineers, that. Moore and Wright also went into what we call digital micrometers. They're not electronic micrometers, they're digital, which means that you read the numbers. So you read those numbers there, and those numbers there will give you a precise dimension there. And you get used to using that. That's not an easy one to use, by the way, but they do work. But it's not an easy one to see whereabouts the markings are. But that was their first move into digital or non-analog micrometers. Just to talk a little bit about the innovations that Moore and Wright came up with. After the Second World War, there was a lot of blind inspectors came back from the war, and they wanted to get into engineering. And Moore and Wright worked with the Royal Institute of the Blind to design a Braille, what they called a Braille micrometer. And we have a Braille micrometer there. Very intricate design, and I've studied how that works, and it does actually work. You've got to understand Braille to be able to use it. So I'd got to learn Braille and then started to use it. So there you can see the range of Braille instruments that Moore and Wright made. We have one in the collection that was given to us by a chap in the south of England, that contacted me and said, I've got a Braille caliper. Would you like it? And I said yes straight away. It's the only one that's, if you go on eBay, you'll not find them. Now that was used by a chap that worked for Rank Xerox as an inspector. He was in the RAF in the war, came back from the war blind, and he wanted to get back into engineering. And Moore and Wright worked with Chesterman to produce a Braille caliper. The caliper is made by Chesterman, and the micrometer head, the Braille micrometer head, is made by Moore and Wright. And I've met the man that was involved in the design of that. He's still around in Sheffield, and he told me all the complexities of that. Inside there is an epicyclic gearbox. So if you strip it down, you'll never get it back together again. There's an epicyclic gearbox in there. So as that turns, it turns a tenth, a thou, a tenth, a hundredth, and these various barrels there are all interconnected. So you can actually read the dimensions by reading where there's a little mark on the barrel. There's a little mark on the barrel that allows you to give a date and position. So as that rotates, it rotates a thou, a hundredth, and a tenth. And you can see the larger micrometers with the same head on, and you can see the depth gauge there with the head on. We have, and it's not in the Moore and Wright catalogue, but we've got one, which is a Braille caliper. This was patented, by the way. Moore and Wright patented the design. And that's a drawing of the inside. That's the drawing of the patent. And you can see the three barrels. You can see the marking across here, which gave you the 0 point. And you can see the locking arm there. When you're using an epicyclic gearbox, you've actually got to lock some of the gears when it's rotated. And that's what that is there. And you can see the complexity of inside it. And it took some brain power at Moore and Wright to come up with that design. Now the guy that did a lot of that still lives in Sheffield. He's not been down to Hawley, but I've invited him to come down and have a look at us. We were looking through a colleague of mine was looking through some drawings that we've got that were given to us recently, and they found this drawing of the engineering drawing of the Braille micrometer. And you can see there, it was 1950, I think, yeah, 1951, that design. But again, you can see the complexity of it and the engineering, all the bits and bobs that go with it there, and the frame and the head. I've got some engineering drawings I want to show you in a minute, just to show you how they've developed at Moore and Wright in terms of their engineering expertise. That's the actual Braille micrometer. That's the photograph of this one I've got. I managed to get a photograph of it. That's the caliper, the Braille micrometer, that that says Chesterman on there. So Moore and Wright and Chesterman worked together. They took a Chesterman caliper, which you've seen before, as a mechanical caliper. They added to that the head, the Braille head. Now you've got to be able to use this from 0 to 1, 1 to 2, 2 to 3. You need a lot of spaces to do that. And I think the next slide shows all the spaces there. So you've got the caliper there, the head there. Then you've got these various spaces that you put in there, and you can measure up to 11 inches. So you can measure up to 11 inches with from 0 to 1 right up to 11. Why they selected 11 inches is slightly baffling, but that's what they designed it for. Moore and Wright also made calipers, and you can see the similarity between the calipers that Moore and Wright made and the Chesterman and the Shardlow calipers. They all came up with similar designs. You've got the nibs there, you've got the inch scale there, and you've got the metric scale there, along there. And that'll be a 0 to 6 inch. Yeah, it'll take about, so you can get up to that distance there with it, because don't forget you've got to keep all this on the scale. So you can get up to about 150 millimeters. Another example of a height gauge made by Moore and Wright. These are what the government told them to stop making, by the way. They said, you're not experts in making vernier scales, which they were to a certain extent. You focus on micrometers and let Chesterman's continue with the height gauges. One of the very major developments at Moore and Wright was the electronic micrometer. Moore and Wright decided that they were going to move into electronics. They could see the way the market was developing. They could see that eventually mechanical analog type measuring would disappear and it would be taken over by electronics. And this was the first, probably one of the first in the world ever to be produced. The man that worked on this lived at Handsworth. He's died recently. He used to come in to see us quite regularly. But he worked on the technology behind this scale here. It's based on what they call Moore fringe techniques. And the Moore fringe techniques is you've got lines, vertical lines, and some at a slight angle. And as you move along, you get displacements. And you can pick up those displacements very, very accurately electronically. So that the Moore fringe technique was used in there. They did a lot of work with companies in London. I think they worked with MPL as well, developing this. A fabulous design. The problem is, it's bulky and heavy. If you look at micrometers now that you can buy electronically, they're far smaller than this. This is quite heavy. It was a success to a certain extent, but it was a fabulous move from Moore and Wright. All disappeared, by the way, when James Neal took over Moore and Wright. All these innovations disappeared. That's a photograph of inside the box. And we have 2 or 3 of these. What I wanted to show was a bit of engineering in terms of the sort of quality of engineering that these companies did. We've got lots of engineering drawings from Moore and Wright. We've not got many from Chesterman or Shardlow. In fact, I don't think we've got any from Shardlow. We've got the catalogues, but we haven't got the engineering drawings. So you can see that's a spindle, by the way, spacing collar for a spindle. You can see the complexity of the dimensioning. Now, don't forget that that's got to be made to a very, very accurate, got to be made very accurately. That shows another engineering drawing, if you can see it, but they've started to use on that drawing what we call geometric tolerancing. Geometric tolerancing, when you design engineering components to fit together, you've got to make sure that everything is precise. Not just dimensions, but you've got to make sure that the angles are right, the diameters are right, the concentricity is right, the flatness is right, otherwise they won't fit together. And you can see on that drawing, I know it's a bit not very easy to see, but you can see they've started to use that sort of technology. This is when Moore and Wright was taken over by James Neal's. So you can see the Neal's name on there. Right, I've briefly gone over what I wanted to talk about. That's information on contacting the Hawley tool collection. So you've got our email address. You've got a website there, an address that you can view